Now we'll be looking at the Kjehdahls process, and Kjehdahls process was introduced by Johann Kjehdahls. Johann Kjehdahls in what year? 1883. And this method is used for the estimation of total nitrogen in organic and inorganic substances. So if I have, say, a food substance, say meat, and I want to estimate the amount of nitrogen in meat, what method do I use? Kjehdahls method. So Kjehdahls method is used for the estimation of what? Of nitrogen in food samples. Do you understand that? Now then, you know, if you check any packaged food you're buying, there's always a food composition table. They say carbohydrates so amount, protein so amount. Then they had nothing to use to measure the concentration of protein. You and I knows that the building block of protein is what? Amino acid, right? And nitrogen is found there, is it not? Now, then what they do is they use the Kjehdahls method to determine the amount, the concentration of nitrogen in that food substance. From that concentration of nitrogen, they have a conversion factor called the Jones factor that they can use to tell you from the nitrogen concentration. They'll tell you, okay, this is so amount of protein found in that food substance. So Kjehdahls method is used for the what? Determination of what? Nitrogen concentration in organic and inorganic substances. Do you understand that? Now, before I talk about the principle, I would like to explain the instrumentation before the principle. Because if I explain the instrumentation before the principle, you understand the principle better. Now, if you want to estimate the amount of nitrogen using the Kjehdahls method, let's say the food substance we're looking at, let's say meat. Now we have meat. Meat contains protein, right? Nitrogen is found there. Now, the Kjehdahls method have 3 steps. How many steps? 3 steps. The first step is what? Digestion. The second step is what? So we have the steps. The first step is digestion. The second step is distillation. And the third step is titration. Alright. Now, digestion is simply you put that substance, that meat now, that substance you want to check the nitrogen concentration in a flask, and you heat it with concentrated sulfuric acid. So digestion, you are heating. You are doing what? You are heating. So you put the sample plus concentrated sulfuric acid and you add a catalyst. And the catalyst used is a combination of what and what? Combination of what and what? Ammonium sulfate and what? Potassium sulfate and what? The catalyst used is what? Copper sulfate and what? And potassium sulfate. Please, not ammonium sulfate. So the two catalysts used can be a combination of copper sulfate and what? And potassium sulfate. So copper sulfate and potassium sulfate can be used in combination. So they can ask you the role, the function of copper sulfate or potassium sulfate in the Kjehdahls process. They are used as what? Catalysts, right? To speed up the rate of the reaction. Now, here, the sulfuric acid here. What is the sulfuric acid actually doing? And remember, we are heating, right? We are heating. How many of you, if you're frying, let's say you're frying egg or frying meat, and you put the oil in the pan and you're heating it, and you put the meat or anything you want to fry in the oil, what do you notice? It will twitch and it will bump out, right? That thing that's as if the oil is boiling and is splashing is called bumping. Now, if you are heating, remember the acid you have here is a conch acid, right? is concentrated acid, and you have the sample here, you add your catalyst and you start heating. There's every tendency for bumping to take place, for that splashing to take place. And once, remember, it is a quantitative analysis. You want to measure the concentration. And once bumping starts, and some of them are splashing out, some of the nitrogen will be lost, right? So to prevent bumping, we use boiling stones. What do we use to prevent bumping? Boiling stones. Some of the boiling stones include what? Glass beads. You can use glass beads. You can use pumice. You can use what again? Zinc granules and other suitable boiling stones. So the function of these boiling stones is to prevent what? Bumping, right? To prevent that splashing, that bumping. The function of copper sulfate and potassium sulfate is what? Serve as what? Catalyst, right? Good. Now, in digestion, we said you're heating the sample with what? Concentrated sulfuric acid, right? Now, if you heat this sample, remember the sample contains nitrogen. If you heat this sample with sulfuric acid, what will happen is that all the nitrogen in this sample will be converted to ammonium sulfate. Once you've gotten your ammonium sulfate, digestion have ended. So the first step, we said digestion. And in digestion, you are heating the sample with what? With what? Concentrated what? Sulfuric acid, right? You add copper sulfate plus what? Potassium sulfate, and they serve as what? Catalyst. Then after the addition of those two things, we add our boiling stones, right? To prevent bumping, we heat. And we said that the sulfuric acid will react with all the nitrogen found in this sample, converting all the nitrogen into what? Ammonium sulfate. Ammonium sulfate. So this ammonium sulfate here is a product of this Kjehdahls flax heating. Now we've gotten our ammonium sulfate. The next thing is we take this product, that is the content of the Kjehdahls flax now, and move to the next phase of our practical. And the next step is what? Distillation. So what we'll be doing here is a normal simple distillation. So if you look at this diagram on the board, this is distillation setup. This is just our retort stand. That stand you always say in the lab, holding the flax, round bottom flax. This is our tripod stand, right? Not this one I'm using to record though. Tripod stand, that one that you see in the lab. And this is our Bunsen burner to provide the heat. Then yeah, you have your, see, this is your Lubic condenser, right? This is your condenser for cooling. You know, the condenser provides that cooling effect so that the gas will return to liquid. This is a collecting container. This is another retort stand holding this Lubic condenser. Now, you take that content of Kjehdahls digestion and put it in this flax here for distillation. And we said, as we put it in this place, what are we putting here? The ammonium sulfate, right? We got from digestion, is it not? We put the ammonium sulfate here, and we add what? A strong base, right? The strong base, most time what is used is sodium hydroxide. So we add the strong base with the ammonium sulfate and heat. So as we heat, you see that they will vaporize, right? And as they vaporize, they will pass through this. And as they come to this Lubic condenser, they will condense back to what? Liquid, into a collecting container. But in this collecting flax here, we added what? A known amount of acid. And which acid do we use? Boric acid. So there is boric acid here. So as you're heating this thing here, you ammonium sulfate with sodium hydroxide. The gas that will be released is what? Ammonia gas, right? Ammonia gas now will now come and be collected with what? Boric acid, right? With boric acid. Now, basically what I've said so far is this. Digestion. You are heating the sample with sulfuric acid. You add catalyst, you add boiling stone. And after heating, the sulfuric acid will convert all the nitrogen in that substance to what? Ammonium sulfate. Now the ammonium sulfate now, you now take it to the next stage, which is distillation. You put it in the distillation flask. And you add what? Sodium hydroxide, right? You heat. As you heat, all the ammonia now we turn into what? Sorry, the ammonium ion we turn into what? Ammonia, right? Ammonia gas. And the ammonia gas is now collected here. But here, you had a known volume of standard acid. So you knew the volume of the acid here. You knew the volume of acid, of the boric acid you use here. But you add excess. So that when the ammonia comes and reacts with the boric acid, we still have unreacted boric acid, because the boric acid we put here is in excess, right? It's in excess. So you notice that some of the ammonia, all the ammonia will react with the boric acid. We don't know the volume of the ammonia, do we? We don't know the volume of the ammonia, but we know the volume of the acid, the boric acid here. So the ammonia will react with some of the boric acid to form ammonium borate. Then we still have excess boric acid. The last stage is titration. And we said in titration, you are titrating what against what? Excess boric acid with what? With what? A solution of what? Hydrochloric acid. So now it is actually known as back titration. You are titrating that to know the amount of boric acid left that is unreacted. So if after titration you've known the amount of acid that was used to babysit the nitrogen. Now the amount of nitrogen used, the amount of boric acid used, the amount of acid used is proportional to what? The concentration of nitrogen in that sample. Now let me run through it again. We said the Kjehdahls method is used to estimate the amount of nitrogen in a sample, right? And it has 3 steps. What, and what? Digestion, distillation, and what? Titration. And we say in digestion, you heat the sample with what? So with what? Sulfuric acid, right? H2SO4. Sulfuric acid. You add catalyst, add boiling stone, you heat. So as you're heating now, we said the sulfuric acid will react with the nitrogen in the sample, converting all the nitrogen to what? Ammonium sulfate. The ammonium sulfate is now placed in this distillation flask, and as it is placed in the distillation flask, you heat. The distillation flask, as you add the ammonium sulfate here, what are you adding next to the ammonium sulfate? What are you adding? Sodium hydroxide, right? It's strong base, typically sodium hydroxide. So as you add sodium hydroxide here and heat, what will happen is ammonia gas will evaporate. So as it passes through the Lubbock condenser, it will now condense into a liquid form and gets into the collecting flask. But in this collecting flask, you added a known amount of standard acid. Standard acid is any acid that you know the concentration. So you add a known volume of standard acid, meaning the acid you're adding here, you know the volume, you know the volume, you know the what? The volume. You know the volume, you know the concentration. Since you know the volume and you know the concentration, remember this formula in chemistry that you are given CAVA all over what? CBVB equal to what? Is it NAMB or MBNA? If you cross multiply, I think. Alright, so if now this is concentration of acid minus volume of acid, right? Now we are adding a known volume of acid. We know the volume of acid. We know the You know the concentration of the acid. The base we are using. We remember we added something here, right? We added sodium hydroxide here. But now, ammonia gas that we are using, we don't know the concentration, we don't know the volume. Now, and the purpose of this determination is to know the amount of nitrogen, is it not? To determine the concentration of nitrogen, we say it's a quantitative test. Quantitative test, you're looking at the quantity present, the amount present. Qualitative test, we're just looking at is it present, is it absent. So now after digestion, you put the whole sodium ammonium sulfate in this digestion flask. Then you add sodium hydroxide. Then you heat. We said what will evaporate, what will vaporize? Ammonia, right? Yeah. The ammonia will now pass through the condenser, and here you have boric acid, right? Known amount of boric acid. It's not only boric acid you can use. It's not only boric acid you can use, but a standard acid. Now, the boric acid will now react with that ammonia to form ammonium borate, right? To form ammonium borate. But we had excess boric acid, meaning some of the boric acid are still free, while some are tied up with ammonia to form the ammonium borate. Now, the last step is titration. And we said in the titration, you are titrating what against what? Boric acid, excess boric acid with what? With hydrochloric acid, and it's called back titration. Now, why you are doing that is you want to know the amount of hydrochloric acid that will be able to neutralize that substance. Now, we say the amount of acid used in that titration reaction is proportional to the what? Nitrogen content, right? It's proportional to the nitrogen content. I'll go over that again, but just know that Kjehdahls method is used to estimate what? Amount of what? Nitrogen. And the three steps are what? Digestion, titration, and digestion, distillation, and what? And titration. And now the principle, what can you say about the principle? The principle is based on the fact that when samples, nitrogen containing samples, react with react with sulfuric acid, that all the nitrogen inside is converted to what? Ammonium sulfate. And that ammonium sulfate can pass through the remaining phases, and we use that to determine the concentration of nitrogen in that substance. So the principle is based on the fact that during digestion, all the nitrogen in the sample is converted to what? Ammonium sulfate. That's the principle there. Let's look at Jones factor. We've seen the Kjehdahls method. That the Kjehdahls method, we are using it to estimate the amount of nitrogen in a sample. Now, the Kjehdahls method, now the Jones factor is a conversion factor that is used to estimate the amount of protein in a sample. Now, this Jones factor, in this Jones assumed that protein, the amount of protein, the percentage of protein, the percentage of nitrogen in protein is about how many percent? 16%, right? That protein contains 16% nitrogen. So if you've gotten the amount of nitrogen, you can just multiply by a conversion factor and you get the amount of protein. And the conversion factor Jones used then was 6.2. 6.25. How did he get the 6.25? So if we said that protein has 16% what? Nitrogen, right? Is it not? Now, 16% percentage means over 100, right? So 16% is same thing as saying 0.16, right? Now, what he did was he took the inverse. He just did 1 over 0.16. If you do 1 over 0.16, you have what? 6.25. Now, if you want to use Jones factor to estimate the concentration of a part of nitrogen in a particular food substance, all you have to do is, first, to get the concentration of nitrogen, what method do you use? Kjehdahls method, right? Now, if you've gotten nitrogen concentration using Kjehdahls method, and you want to get the amount of protein, what do? Times what? You just use that nitrogen concentration you got times what? 6.25. But then anything you get, you now say that is the concentration of protein in. So the application of Jones factor. Jones factor is applied in the determination of protein using what? Nitrogen present. But this method is faulty and is no longer used. Alright, so Jones factor was faulty because they are now multiplying off first of all, nitrogen. Not all nitrogen in a food substance is part of amino acid. But here we are assuming all the nitrogen in food substance is out of the amino acid, which is not correct, first of all. So now they said instead of multiplying the amount of nitrogen by 6.25, we'll multiply by a conversion factor that is peculiar to that food substance. So if you go online now and type Jones factor is not just 6.5. If you type Jones factor for rice, somebody should try it. Let's say Jones factor for beans. Type it. Type Jones factor for beans. Jones factor for beans. Jones factor for this. They have different numbers. Who have seen the Jones factor for beans is what? Somebody should type 6. What? For beans 6.25. Somebody for rice. Does rice have protein? For rice 5.3. For beans is what? 5.7. For rice is this. For fruit, so you see that rice is what? 5.95. Say milk is 6.3. So you see that we have different Jones factor for different substances and not just multiplying by 6.25. So check now for Gary Eba. Alright, so basically you see that if you are asked to write on the application of the Kjehdahls process, Kjehdahls process is used to estimate the concentration of what? Nitrogen, right? In food sample. But now Jones factor is used to do what? Is used to estimate what? Protein using the nitrogen concentration. Now I gave a formula. If you want to calculate after your experiment, if you want to calculate the amount of nitrogen, percentage nitrogen, because it is amount of nitrogen we have that will now multiply by the Jones factor, right? Percentage nitrogen is equal to what? N times what? V times what? Times what? All over E. This is the formula to estimate that. N here is normality of what? V is the volume of the acid, right? Used. Then 14 is the mass of what? The atomic weight or the molar mass of what? Nitrogen, right? Nitrogen is 14 now. 100 here because we are looking at percentage. Then M here is the mass of the what? Mass of the sample. So before you even start your experiments, you must measure the mass of the sample. Then if you use this formula, you will now get the percentage nitrogen. Then if you want to estimate the protein, you say this percentage nitrogen times that conversion factor. So basically, that's that. Yes.